Hello, everyone. Today's talk is will be delivered by Professor Priyanka Das. She is an assistant professor at IIIT-Bangalore. She joined IIIT in 2018, prior to which she completed her PhD from IIIT-Bangalore. Before that, she received her MTech degree in digital signal processing from IIT Guwahati in 2011. BTech she pursued in radio physics and electronics from the University of Calcutta after her BSc degree in physics from University of Burdwan. She worked in Nokia Solutions Networks as a summer intern and Dell Research and Development Bangalore as software associate engineer from 2011 to 2012. And her research interests include spectrum sharing networks, MIMO, physical layer security, and intelligent reflecting surfaces. We'll welcome her to start the talk. Thank you.
Thank you, Professor Vinod, for the introduction. Welcome all for today's Samvaad talk. Today, I'm going to speak on intelligent reflecting surfaces, fundamentals, optimization, and insights towards 6G wireless networks. This is the brief outline of my talk. First, we will be focusing on what is IRS or intelligent reflecting surface. To start with, we will see a basic applications, which is very popular for IRS, that is the coverage extension. We will see how exactly IRS is helping us to extend the coverage area of an user equipment. Then we will focus on the spectrum sharing network, and we will see what is the utilizations and what is the need for it. And then we will see how exactly IRS can be fitted in the spectrum sharing network. And we go into our problem statement, result, and discussion. So today in the era of beyond 5G and we are going towards 6G, massive MIMO is a reality. So when we talk about massive MIMO, we talk about more number of antennas. Basically, the more as you increase the number of antennas at the base stations, the price you have to pay in terms of energy utilization. When you increase more and more number of antennas, that means that you are also going to tolerate more radio frequency change. Of course, the positive aspects of it is huge. It increases the spectral efficiency. It turns out that your data rate, which is a major concern, which will be aggressively increasing when you talk about more and more number of antennas. But nothing is free. So of course, we have to pay something. And that's what we talk about, the cost, hardware cost, complexity, and energy consumption. So putting this point into our mind, now next question is what can be the next thing? So in sixth generation wireless communication systems, we are expecting soon one promising approach that all over the world we are talking, that is called intelligent reflecting surface. Now, when you see a reflecting surface, what is a reflecting surface? Basically, from our physics in the undergrad, we know the Snell's law, that is, if there is a mirror, it is nothing but a reflecting surface. A signal is coming in and it reflects following the Snell's law of reflection. Now, what exactly IRS is? We talk about it's a reflecting surface, but not only reflecting surface, it has an intelligent name before it. So exactly what it is doing. So let's talk about that. You have a transmitter over here, and this is the intelligent reflecting surface. What is this? So it nothing but it consists of large number of small reflecting elements. The size of the reflecting elements is of the order of the wavelength of the signal that is going to impinge on. So you can think about maybe 30 to 64 elements are there. And what it is exactly doing, the signal is coming in, and the reflected signal is not only the incident signal, but there is a the coefficient which we called the reflection coefficient. It changes, or we are going to change the reflection coefficient such that wherever I want a high directivity, it will provide a directive signal by controlling the phase of the incident signal, and it will provide a directed signal towards the user that you are going to serve. Now, there are basically other names for IRS. So sometimes we will see it's called software control meta surface or reconfigurable intelligent surface. Let us see what it talks about. So unique features of IRS. So as you can see in that picture, that basically there are small number of reflecting elements with some special features. What are the features we can have? It, of course, it is phase shift can be adjustable. Not only that, it is nearly passive. So as opposed to the MIMO, when we talk about the active elements, the IRS is passive because it is just a reflecting surface. And we do not need to have the dedicated energy source for the signal processing. Like you do not worry about the amplifier, decoder, analog to digital converter, which we typically focus when we design a transmitter. So it does not need the decoding or encoding. It's nearly passive. And due to the passive nature, it is not amplifying the noise which is associated with the signal that is received from the transmitter to the IRS path. So it is not amplifying the noise. So this is another advantage. Now, it is particularly useful when we will come to the scenario when the exact line of sight link is blocked. That means you are not expecting the direct communication is there between the transmitter and the receiver. So now we are going to compare how IRS is different with respect to massive MIMO and something called relay-based communication. So let us focus on the old technology that almost 10 years old, that is called relay. So what a relay does, you can see that there is a base station and there is a relay, which is nothing but it tries to forward the signal from the base stations to the relay. It receives the signal H into SN. What is SN? That is a transmit signal. H is nothing but the wireless channel coefficient. Now the relay takes the signal, it amplifies with a coefficient called beta, and the received signal multiplied by the channel fading, it will have here. So functional wise, so the relaying is a active component. So it is not a passive component. It also tries to forward the data. It's not a reflector. It has a capacity that it will either do amplify and forward or do decode and forward. So that's how the relaying works. In terms of hardware complexity, of course, a dedicated power source and RF equipment is needed for its operation. When we talk about the relay, it's costly because we talk about the power source, RF equipment and all. And also the other pain point that we have to tolerate is the noise amplification, because let's say this channel is too noisy. If the amplitude is multiplied by the factor beta, so the noise will also be similarly multiplied by the same factor beta. So you will get, you are basically amplifying the noisy version of the signal in the case of simple amplify and forward structure. Now, let us look into the other futuristic technology here. So, RIS is the same as IRS, just the same name we are interchangeably called. It is intelligent reflecting surface or reconfigurable intelligent surface. So, it's not equivalent to a relay. Why? Because you can see that whenever there is a IRS, what is the difference here? So you can have a amplification, so it is the coefficient beta, but you can see there is a theta. Theta is nothing but whatever signal is received by the IRS, it is going to be phase shifted by this, and theta captures all the phase shift matrix for the n elements IRS. So it's basically a matrix, and it is multiplied before this. So you get the transmit signal, the reflected signal after doing the so basically theta captures both some kind of an attenuation component plus some phase shift change of the incident signal, and then it will receive at the receiver end. Okay, so what is the other way around? We can see that since it is nearly passive, so we do not need to worry about this complex processing over here. No dedicated power amplifier mixers are required. And what we need is small low-cost elements which are suitable for nearly passive implementation. Okay, now, of course, nothing is free lunch. So we have to really see what IRS needs for its better performance for the upcoming 6G. Now, before going into the extra things that we have to pay for in order to implement this technology, let us also compare with our second friend, that is the massive MIMO. So when we talk about the massive multiple input, multiple output systems, again, we have a massive MIMO base stations, which can think about of the order of 32 to 64 antennas, and it is serving, it creates a beamform, and it serves the users by using the MIMO beamforming technique. So it needs, of course, multiple antennas. So we have to tolerate this multiple RF chains needed for more active elements, and it has an increased energy consumption hardware cost. So when we talk about how do you basically duplicate or how do you get similar or almost similar performance benefit, which massive MIMO base stations is providing, people are thinking about putting these mirrors or reflecting elements along the facets of the tall buildings. And what will happen is, let's say the base stations, it sends the signal and it's going to be reflected by this IRS, and we are going to see how it is doing the beamforming to serve the users which are located surrounding the base station. So so this is as compared to the massive MIMO, we have seen the advantages already. Now, so the goal is IRS-aided MIMO system allows base station to be equipped with substantially less antennas without compromising user quality of service by exploiting large aperture of IRS to create something called beams, okay, which we call the passive beamforming. Now, what are the typical use cases of this intelligent reflecting surface? So to the nutshell, you can see that multiple applications we can think about. So one will come one by one. So you can see that there is cell edge users maybe which are far away from the base station, and from the base station to the cell edge user, it can come via the reflections through the IRS, which is fixed in the tall buildings. We will also can think about the localizations. For example, the direct link from the satellite to the user is missing due to some obstacle. So it can come via the reflections to this building from the base stations to the wall, and this reflector, and this going to reach to the user over here. We can think about the transportation system where whenever we talk about there is a base stations and no, the connection is not there, so it can connect the user, which is maybe the mobile user traveling, the connection may happen through this. And also IRS has a promising approach in the indoor environment, which is the smart office, where you can see these blue patches, which are nothing but the IRS, and it is creating a beam, okay, which we call the passive because it does not really involve active elements. We will see that some other cases also, which can be the SWIFT or something called physical layer security. So there are multiple use cases. So we do not understand all things together, but let us focus to some basic, simple application. Yes.
Yeah, because it's a massive level. For that, it is low, but you think directly on road in the ground.
Attenuation, we normally, yes, attenuation will be there. We have the reflections, but we will try to mitigate the attenuation effect by putting multiple IRs. Beta factor is there. Typically, it is less than 1, which we call the normalized version of beta, output by input power. It is 1, but it can be mitigated. That's not a serious problem. What is the problem is how to control the phases of the signal rather than the amplitude. Even if you have amplitude factor less than 1, trying the, so we will see the constructive interference and destructive interference, how this beam forming is. Yeah, please. We will come to this. I will come to this. So that's what is the basics. Yeah, so I will go to the to answer Professor's question. We have to really go into the depth, and we'll see how IRS is acting here. So let us consider a simple model to start. This is maybe a dumbest possible simplest model. You have a direct link which is blocked, maybe a tall building or something is there, and there is a IRS, and you can see the IRS is normally located along a altitude. Height is there, so the signal is going and after coming back by the reflections through the eye. So how do you model this? So let us assume some parameters. So n reflect elements can be adjusted according to the channel phase. So what do you mean by this? Total number of elements, let's say this is n. Now, what is a typical system level equation? See this, notice carefully. So we are also understand basic physics. So this is your transmit signal X, and let's say the power transmit is P of T. So R captures the received signal strength. So power, square root of power, basically this is the amplitude. So if I do a square of it, it captures the power. And this factor captures the path loss, which is basically it has to traverse the wireless channel. Depending on the distance located, we will have some terms. If the distance is more, typically the path, this factor will be, there will be attenuation due to the path loss from this traversing this path from this source to the IRS. And depending on how many IRS element, let's say n equal to 1. So typically what will happen, your X is getting, it will multiply by the channel coefficient from the source to the IRS, which is HSR, into it will give a phase shift, which a term we captured by e to the power j theta. So normally we write some beta into e to the power j theta, where beta is your attenuation drop. And here beta factor is omitted. We have made it 1, but typically beta is a number. Right? That captures the attenuation loss. So neglecting the beta term, what we are interested more is the e to the power j phi I, which is the phase shift for the ith IRS. Okay, and then it will reflect by all the reflecting elements it will do. So that's why sum over I1 to n, and of course you also have a signal from the IRS to the destination, and that's how this particular channel is showing up here. So, so if one element is there, I will have only I, sum of I equal to 1 only. So a lot of elements, so it is sum over all this. So now if we try to understand under what case of phi I will get a constructive signal, or all these signals amplitude, total aggregate amplitude will be the maximum. That is one of the questions. So let us factor out the channel terms into the corresponding amplitude and the phases. What is that? This is the channel from source to the IRS for the ith IRS reflecting element. And this is similarly for the IRS to the destination for the ith one. So if you substitute these and these two over here and doing the basic things, you can simply manipulation, you can tell that this is alpha I, beta I, e to the power j phi I. So what is this delta of phi I? This is basically nothing but it is, if you substitute this, so you will have a already phi I is here and you have this coefficient. So I can aggregate the composite phase term separately and the amplitude term separately. And now I will be asking the questions under what condition of delta phi I, my signal strength is the maximum. We talk about the signal to noise ratio, that is the signal power is the maximum. So this is the very basic question to start with. So the it starts with this: find out the condition. How do you choose the phase shifts such that your SNR is the maximum? So that is what conditions we know that when delta phi I is equal to 0 for all this I1 to n, where n is the number of IRS reflecting elements. So this is the condition number 1 where we get that, okay, so if I have to get the maximum SNR, which is this quantity, what I have to really ensure is this IRS phase shifts has to be equal to this condition. So this condition has to meet. So every phase shift is related with the phase of the incoming signal and phase of the outgoing signal. So I have to really monitor the channel strengths, find out this phase, and according to that, I have to optimize the phase induced by the IRS such that total phase deviation is 0 and I get the maximum SNR at the output. So this is theoretically, we get the delta phi 0 conditions, and which gives the gamma max, which is the maximum SNR, which is of this form. Okay, so this you can see this is appeared in this TCOM paper in 2021, the basic fundamental study of IRS and how it really captures in scenarios. So we will study two model. This is from the paper, same paper. So what it is telling that you want to capture the path loss. Path loss for what? You have the blue line. So these are for two different frequency range. One is the low frequency, we called FR1, 2.4 gigahertz, and another is the high frequency range, or FR2, which is 28 gigahertz, typically millimeter wave set. So we plot the path loss. So what is telling, as a function of distance, the horizontal distance from the source to the IRS. You increase the IRS distance from the source or the base station or transmitter, the path loss is more. That means what is a path loss? It is the transmit power minus path loss is your received power. So as your distance is more, you will feel the signal is deteriorating or path loss is higher and higher. Now, this is the case when I have line of sight, direct line of sight. This is the case when I have non-line of sight. And when I embed the IRS in between, you can see they are in these curves fall between this and this. And also you see as the number of IRS reflecting elements is increasing from 64 to 256, you are reducing the path loss. So effectively, it is helping to reduce the path loss in this frequency range and also in this range, but you see that you have to really go slightly higher number of IRS element if you want to really have a greater improvement of path loss in FR2 or millimeter wave regime. So take away message from this, the capturing the path loss in turn will also decide what is the path loss coefficient. That is, we capture to model the path loss model, to write the path loss model. So as you increase the IRS element, you can see the path loss factor, which we called PLE, this factor is actually reducing. That means what? Path loss factor reducing, meaning you have better signal strength. Okay, path loss is more, meaning signal is deteriorating more. So as the number of IRS element increases, your path loss is reducing, and it is not reducing that much drastically, but slightly at a lower rate with increasing N in the high frequency range, because high frequency range we have other perturbations from the atmosphere. The coverage area is relatively low. So from this, we can take a message that yes, IRS is trying to help the change of the wireless environment by reducing the path loss factor. Okay, this coefficient, which is very important in modeling the delta, this path loss, or whatever we did in the last slides. So by thinking that, okay, it is doing in the correct directions, that it is trying to help us to control the wireless channel intelligent way meaning that is the beamform. When we say delta phi 0, basically we are trying to align our signal in a coherent interference manner so that we get the maximum boost up in the signal at the receiver. So application wise, you can think about, you talk about an indoor environment. So for example, there is a source, the direct line of sight connection is not there. So you can actually survive the destinations by reflecting multiple IRS coefficients. So, and also sometimes we can think about what happens if I divide a large number of IRS. Now, it is only one IRS with more number of elements, or I fragment into this. Okay, so there are another studies which people talk about, and another important terminology, we can see that the probability of error, which is one of the performance metric, that's actually exponential minus ns into n whole square. So it is actually, if you increase the ns, which is number of IRS element, and n, which is one element has how many reflecting coefficients, it's actually trying to capture both. They are more, it's actually falling to the power n square. Okay, so it helps in reducing the error performance. Similar situations, we can think about what will happen theoretically for the outdoor environment. So this is my source, this is my destinations, and you can see some blockage is there. So you put one IRS very close to source and one IRS maybe close to destinations. There might possible that this destination user is getting a better quality of signal strength. And similarly, we can large number of reflecting elements can have multiple IRS with this. So that's the optimization problem, that where do you place this IRS and how many IRS are needed in order to support the area users within a vicinity of a base station. So these are the problems that people are looking into. So IRS selection is, and also when more IRS elements are present, it will also be a good idea that you pick up the best IRS, not only because you know that in order to perform better, I need to control the phases accordingly. So that's a overburden that I need to control the phase of all the reflecting elements of all the IRSs in a very perfect way, such that I will exploit the benefit of the beamforming. So now with this basic example, I am going into depth, which we did in our work, in our lab with the MS student, focus on a relatively not explored area in the context of IRS, that is called spectrum sharing network. So the concept of spectrum sharing network is also not very recently. It is almost starting from, yes, please. Yes. Yes. So when we have multiple, yeah. So when we have multiple users, we typically formulate a metric which is the sum rate, or sum throughput. So and then we want to maximize that, or we want to formulate a problem. How many IRS elements do you need such that the total sum rate is maximized over that users? Yes, yes. Depending on what kind of quality we want to estimate. Typically, the sum rate or is a measure where we talk about multi-user scenario. And here we are not talking about multi-antenna so far. So that complexity we are not going. Single user, single base stations, single user we focused. If we have a multi-user, we have to think about what is the rate individual is happening, then sum up with this, and we want to maximize this. And the problem again will be the phase shift optimizations of the IRS. Complex. The complexity level will be higher. So we will start, that's why we will start with a simple problem, see how much complex we are, we can solve it or not. Then the multi-user can be an extension for this problem. We need to control the phase shift induced by, so let's say this phase shift is theta1, theta2, theta capital N, theta 100, let's say. So I need to control theta 1 to theta capital 100, theta, this matrix, capital theta matrix, depending on the wireless channel. So we have the complex valued number. Both. Yes. So that means, so when let's say there are two signals, if I go back here, right? We are here. Now you can choose your phi I in another way as well. Now my question is, what do you mean by array gain? This is my signal that I am receiving at the receiver. Whatever I have to do on it. By controlling, what can I control? HI, SR, HIRD, these are cannot be controlled. This is basically the channel. If the channel is strong or weak, they will be according to that. This is my transmit power. I have no control. This is also I cannot have control, depend on wavelength, frequency of operations, distance where it is. So whatever controllable element is this phi. And the phi is chosen, it is theta plus psi, such that I will get the maximum value out of it. So that's what we mean that I am receiving n such signals and I want to make a constructive interference. So that means that the total aggregate, they are in phase with respect to each other. So similarly, I will talk about out of phase conditions where I do not need a constructive interference. Maybe I need a destructive interference. Yes. So array gain in the sense we that's what we talk about. So we are getting the SNR as the number of elements are more, our performance is better and better. So that's how we have a array gain. And that also you captured by e to the power this form, ns into n whole square. That's what. Okay. So I will, yes.
You have multiple users. You also then need some constraints, right, to make sure that the SNR for every service about.
Yes. Yes. So yes.
Be a normal, only an unconstrained output.
No, it is a constraint optimization. Yeah. Sorry for yes. So let us see what is this spectrum sharing is talking about. So typically wireless spectrum, when we talk about the lower frequency range, it is very crowded. But although it is crowded, it is not utilized for most of the time. Let's say the TV white space. It's not utilizing for the most of the time. So the concern is why can't other users which are not licensed, they can use the same spectrum, which is vacant, anyway not using, let me use the other one. There is a challenge for it. You can actually make sure both the primary user and primary is the license, they have paid. Secondary not licensed, they had not paid. They can transmit at the same time, but at the time, secondary transmission will cause interference to the primary, which we do not want. And this interference is actually a pain point in the spectrum sharing network. When we talk about underlay mode, it is basically telling they can do simultaneously in the same spectrum, but you have to tolerate this interference. The challenge is the interference will put a transmit power constraint on the secondary users. If you are interfering too much, I will not allow you to transmit at a high power because your interference power is proportional to the transmit power at this end. So obviously secondary transmitter is forced to transmit at a lower power, and that's how the secondary communication is limited, or I cannot have a much wider coverage area for the secondary users, although it is helping the primaries are helping them to actually communicate in the limited spectrum simultaneously. So this is the problem. Now talk about IRS here. How does IRS can help the communications of the secondary network? Whereas the primaries are happy, they communicate with respect to each other, they have the spectrum, they can transmit at any power with the budget, they can do it. But secondary transmitter and secondary receiver is here, and IRS is there, which is basically sitting to help the secondary communication. So what is the this controller doing? This controller is basically telling you need to control the phases according to the channel estimate. That's how it will give the command to the IRS. Hey, change the phase according to this phi I will be theta I plus I. What is theta I and psi I? That base station will feedback. It will control the phases. It has to be done once in a coherence interval as the channel is changing, depending on it's a slow fading, fast fading. Now, what is the problem, extra problem this spectrum sharing network has to tolerate? You see that if I place a IRS, obviously I get a direct signal. It may be blocked, may not be blocked, and a IRS reflected signal at the destination. So I can do a passive beamforming such that this signal and this signal can add up, and I will get a better performance for the secondary network. Now think about the primary. Whenever IRS is sitting, now it is also creating extra interference to the primary receiver because I have a direct interference channel and a IRS aided interference channel. So I am actually creating more interference. Whether it is helping my secondary, at the same time, it is also damaging the primary this thing. So that's the point. So catch is primary user point of view causes more interference at the primary receiver X via the IRS aided reflected link. And of course, you cannot do this. You cannot make this happen. So you have to satisfy the interference constraint. What is this? What is this? How do you do this? Come to this optimization problem. Need optimal control. So now IRS phases are controlled not only to improve its own communication, but also to make sure the interference at the primary receiver is meeting its constraint. Now, what is the interference constraint when you talk in the spectrum sharing network? So there is a lot of literatures are there. People go into the 4 major categories. Depending on what kind of quality of service primary will satisfy. Peak interference constraint, it is every point of time you need to satisfy the interference power should be less than some value. Let's say maximum interference power is 15 dB. You are not allowed to cross the 15 dB limit at the primary receiver, strict constraint. Average constraint, on an average, you can do 15 dB, 20 dB, 9 dB. On an average, you have to satisfy 15 dB. primary SINR based constraint, it is something like that. It will check what is the SNR of the primary link, and primary SINR should be above a threshold, because I need to also make sure primary is the licensed user, their communication should not go down. Okay, so I will focus on here, okay, average interference constraint in this talk. And yes. So actually the based on the interference it produces. Yes. We cannot make sure like that. Yes.
The maximum ARS that you can get to get the upper end of that, to get the power is less than
yes, that is one of our criteria. Yes, you are right. Yes, you are right. Now, but sometimes you will not meet that constraint. If you meet, then you are happy. If you meet, then you are in the back to your own regime without spectrum sharing, and you do your best thing as you are telling. It's an optimal solution. We will also see that. Yes, so your interference will also get from the transmitter to the IRS to the destination. In this somewhere else meaning, one is this to this, T to destination, another is the reflected to this. Huh. Reflecting. Yes. 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 And it can also, yes. 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 So it will deteriorate the signal. Yes. Yes. So if I consider the secondary user signal to noise ratio point of view, signal power will be determined and it will have an additional interference power coming from the primary transmitter via IRS to this. Yeah. So I will come to this little map. We will first set up the model first. So this is the problem that we considered, that the same system model diagram. So let us see this. So what a simple setup, a single antenna model here. Everyone is single antenna, no MIMO here. IRS consists of M reflecting element. We model the channel from HSR, HRD, HRX, this one. These are assumed to be Raysian feeding. Now, I'm not going into what is Raysian and all. It's another model that captures both. You have a LOS and NLOS path, line of sight and non-line of sight. Okay, so depending on the terminology, this is my mean, and this is a factor that captures how strong is the line of sight path compared to non-line of sight path. So for this, our problem is this. We want to minimize the average symbol error probability. This captures a symbol error probability expression, which is function of two things. One is what is the power of the secondary transmitter, and what is the phase matrix. This theta is the IRS phase matrix, okay, which you have to control. You have to control jointly the power and the phase. And we consider a simple scheme that is called binary powered control, just for easy to implement to get the closed form solution. And it also has a practical implications that you do not need to control all over the range. That is a continuous powered control. Here the power possible either on or off, the dumbest possible thing, which reduces the complexity of the power amplifier design. basic thing. And then what is the constraint? This is actually the average value of the interference power to the primary receiver, and this is an average interference constraint. Average value should be less than a threshold. And the power we talk about 0 and Pmax. It can be anything on. If it is Pmax, it is called on or off. So for this, look at this. What Professor Vinod was talking is this scenario. If you can find out a case, let's say you transmit with the full power Pmax, and we okay. So before this, okay, sorry. This is we look into two aspects. One is under what phase condition the IRS will produce minimum interference power at the primary, because now I have two objectives. One is ACP minimization. Interference also has to be less than the threshold, average interference power. So I am checking what is the phase condition such that the interference power at the primary is minimized. This is from your basic pi destructive condition for the phases, that is a phase difference of pi. And then using this phase, you can compute the average interference power, which is the minimum condition, which is the minimum value. So you can see something A minus B whole square is coming up, some formula is coming up. Okay, this is one case. Now we are just seeing the scenario what can happen, and then another scenario when we talk about minimizing ACP condition. What is the IRS phase which will produce the minimum ACP condition? That is the earlier as before, that when delta phi I is 0, you choose the IRS phase, which is the phase of the direct path source to destination, secondary minus source to IRS plus IRS to destination, because e to the power j phi all will be addition and subtraction. So in this case, you compute using this, you compute what is the interference power on an average to the primary, using the best possible condition for the IRS phase for ACP minimization. You find out what is the interference power. If it is well below my threshold, I will be happy, and then I will be keep using this. So that is one situations which we now we are formulating the optimal policy for this optimization problem, that optimal value of PS and theta that minimizes the average ACP while satisfying the constraint is given by this. When the average interference power is less than threshold, whatever phase I have chosen, if I compute the average interference and if it is well below the threshold, let's use it. It's the optimal rule. Okay, what is the catch? This is also called unconstrained rule because it is the same conditions we are now in the without spectrum sharing. That's a conventional policy. Catch is, yes, you have to monitor what is the phase of these channels accurately. Okay, so channel statistics of and in order to compute this, you need to know the channels to the source to the primary, statistical based. Now come to the more dangerous case, when your I unconstrained is not satisfying the constraint. What you will do? Formulate a KKT condition, and our simple constraint optimization problem, you have to minimize the objective function plus Lagrange multiplier times the constraint. What constraint we have? Average interference constraint. Formulate this, and our we have not shown the proof here. It is proven that this policy, so it is you need to jointly find PS and theta, choose the optimal value which minimizes this objective function. This is called, let's say, some metric, selection metric. How do you choose lambda? Lambda is chosen such that whatever average interference is meeting the constraint with equality. That's the standard KKT conditions, the constraint, the Lagrange multiplier obtaining condition. And this is the paper where we solve this. Now, this is something more complex to do. You can see we do not have a closed form expression for either PS or theta. Earlier case was very simple. PS was Pmax, theta was this. Now it is a something, some function is there. PS can take two value, but theta can take multiple values, and it's a matrix, and matrix has that many elements, and each element can have phase zero. A lot of phases can possible, continuous phase or discrete phase. So this is a, although this is an optimal policy, the optimal policy we did it. Try to come up with the algorithm to find out this, but this one, the complexity is huge. Even if you talk about only 4 possible phases, I will allow, not 100 phases. So the complexity is exponentially increasing. So we also do the coordinate descent algorithm, which is a suboptimal scheme, but with a lower complexity, that you can obtain the phase and this with O of M, where M is the number of IRS element. Okay, so yes, so this one, this is it will not fall under convex optimization. Yes. We have not, I think it will not fall under convex optimization, this tool. Why? Okay, let us go back to the metric. So when we mean the convex problem, so that means this one so this is a, first of all, this is a couple problem. It's a both two parameters are happening. One is takes two values and one takes a continuous values, theta, and it is only two values. And it is sitting where some exponential of this, and also this, what is the gamma s? Gamma s is not a linear function. It's again a quadratic function, something square. And about this one, this expected value, this is again a quadratic. Inside the I, it's a something mod square. So expected value, convex sum. It's a sum. But I'm not sure how PS and theta jointly can be done out of this convex solver. When we have single variable and maybe this one, but jointly. Yeah. Then we are then your suggestion can be a closed form solution is the. Yeah. You should be able to find the like you said, it took exponential number of. Yes, brute force, brute force. If it's complex problem, yeah, I have not explored into this. I was talking with Professor Raghuram one day, and he was suggesting this, but I am not sure about this. So we went into the KKT condition standard. So earlier in our one of our problem, we also have similar kind of thing, but that's the optimal solutions, that e to the power this thing. But how do you get it closed form solutions, that we don't have any answer? But you are telling at least you can obtain numerically. Quite efficient. No, but in this problem, we were trying 10 IRS element. and each IRS can take maximum 4 to 5 phases. So when we talk about n to the power m, so m is the number of IRS element and n is the, let's say, 4. So 4 to the power 10, that's how its complexity grows. So that best we can do here. So that was the pain point. Yes.
Yeah, and like for example, if you do something like complicated. Yeah. It will be fine. No, it will actually guarantee convergence in exactly in the number of steps exactly equal to the number of dimensions. It will be linear.
Okay. Yeah, that's one thing maybe we can explore. That's why I told my student to take optimization course. Lohini will be carrying forward this problem for continuous power control. So what we did this, CDA we have checked coordinate descent, and the selection metric actually converges soon. We have seen that number of iterations with that many, we are getting almost saturations in the selection metric. In the coordinate descent algorithm. So it is faster, but coordinate descent, again, it is not the optimal. We go ahead with the complexity problem, and we try to come up with two closed, it's not optimal, but it's really doing greater, almost close to near optimal case. One is called the minimum interference rule, which is the same thing where theta is chosen, the phase shift is chosen to provide the minimum interference. But the problem is whenever you choose this, you need to also get the powered control policy. So this powered control policy we opted where we transmit power to the full power when G is basically the interference, composite interference channel under this phase condition to the primary is less than alpha. And how do you choose alpha? That's basically whatever is your interference power, average value, take the value to ITH. So this is one policy. This is called minimum interference policy, and we have some plots. We compute the PDF of GMIN from theory and analysis. And I will go to the result. Maybe we will see that another rule we propose, that is a minimum SEP rule, where we just go ahead and choose the phase in order to minimize the SEP. But obviously, it will violate the constraint. In order to meet the constraint, you choose the Pmax, power Pmax to a certain value of G, that is 0 to beta only, you choose, otherwise 0. So you forcefully, you are actually making your power to shut down for more often by using these two suboptimal policies. So let us go to the results, what it is telling. So we have to also analyze what is the interference power impinging at the primary receiver. And this one, you can see that we have to meet the constraint. So whenever this I unconstrained is basically, if you do not follow any, just pick up the best phase for the best SEP condition, this is the interference. You are going to hit the interference power almost linearly as you increase the power, transmit power Pmax. And but you have to meet the constraint. So let's say the constraint ITH is 10 dB. So our policy will make sure that you will go each here and it will saturate, it will not go beyond 10 dB. When your ITH is 15 dB, it will go here and it will saturate at 15 dB. So it is meeting the constraint. This is the optimal policy generated interference power at the primary. Now, when we come to the SEP comparison, SEP plot, so you see that we have two region, right? Region 1, which is unconstrained, and this is constrained. So what will happen for low values of power? Your interference power is low. So you will be choosing the best theta compared to the SEP minimum conditions. And as the power increases, SEP will fall down. After certain value, when you are actually in the hitting the region 2, where the KKT condition based rule is kicked in, you try to low little bit down, but suddenly you see, as my power is also shut down for more often because I have to meet the constraint. This power policy is reaching to certain extent that after a certain value, you will see the SEP is no longer decreasing, it starts increasing. And at the high SNR, at the high transmit power, it saturates. So this is, if I do not have a spectrum sharing, it will continuously decrease. If I have a spectrum sharing, in order to meet this, my SEP should increase because I have an interference constraint to satisfy. This is because of the binary power control policy. We are expecting if we use the continuous manner, we can vary the power. We should not get that deterioration as fast as this. Okay, now come to the performance benchmark. So our optimal policy is actually here, which we are plotting. If I increase the threshold of the interference, what does it mean? The lower threshold meaning it is tighter constraint. Higher threshold means you are allowed to impinge high value of interference power, which is a relaxed constraint. So tighter the constraint, you are in the region 2, where the KKT condition is kicking here. So you are here, and you can see that it is decreasing and saturate. Why saturate? Because your interference power is, the interference threshold is very high, but your transmit power is fixed here. So for a fixed transmit power, it does not matter what is your threshold is. If your threshold is too high, it will only give you the SEP to whatever your maximum transmit power is providing. So comparison for this, so we compared with our policy. This is my optimal rule. MI rule is here. MI rule is doing almost, out of all this, MI rule is better in the region 2, but region 1 it is here. The AIM SEP rule, which is always you choose your SEP minimum theta. Don't worry about this. It is actually giving you the similar performance of the optimal rule in region 1, unconstrained region, but region 2 you can see it is bad. No IRS is here. So sometimes you can see no RIS and all these rules, they are almost giving the similar kind of performance here. So now optimal rule outperforms by 1 or 2 orders of magnitude. MI rule is near optimal in region 2. And the minimum SEP rule is almost near optimal in region 1. So I cannot have both regions. The suboptimal rule performs better. Now we also characterize, we are talking about the power control. What is the probability that transmit power is 0? Or what is the probability you are shutting down the power? So you increase that. Here what is happening? Probability of transmit power 0 is more when your interference threshold is lower. That means when it is tighter, you are forcing the power more often. You are forcing the power more often when not optimal case lower value, all the other case higher value, and that's how this SEP degradation is also up here. Okay, so this is corresponding. This is confirming the reason for this. We also try what will happen if the distance between source and destination is changing, where IRS is located at 40 meter and source destination is actually varying. We are moving the destination from the source, and you can see that when I have no IRS, as you increase from source to destination, distance increases, average SEP increases, which is performance basically degrades. But if I have a IRS, basically if I talk about 100 elements, I can see the as the distance increases, IRS is located here. So if source, if the destination is close to IRS, I will get a sudden benefit due to the IRS thing, and my SEP reaches the minimum value. And again, when destination is away from the IRS, okay, this is my IRS location, 40 meter, destination is 60 meter or 55 meter. Due to the distance path loss, again the SEP is high, which is the bad case. So we can see that yes, the position of the IRS matters a lot. And also here what we did is IRS is actually moving fixed source and fixed destination. We have observed that when IRS is either close to S, So this is DSR, distance between S and IRS. So it is close to S or it is close to D. We got a dip. Otherwise, it is more. So this particular regime will be the matter of fact where you place the IRS. Sometimes we also focus into other kind of quality measure for the secondary network, which is also important, is outage. What is the probability that SINR below a threshold? Okay, and we also plot all the results in the form of the SINR, outage probability versus ITH, and we see almost a similar curve that this is the optimal rule. This is the minimum interference rule. No RIA. So fixed phase and random phase is something where you just make sure your only one phase is choose, or the phases are chosen uniformly, randomly fashion. Okay. Now, sometimes people will ask that IRS elements are very close located. So there will be effect of correlation. And this correlation meaning you cannot think about your channel from source to IRS are independent in nature, but they are correlated. And that's how we compared the SEP for different position of the two elements, nth element and mth element of the IRS. They are located so and so. And you see that as the location value, the distance is decreasing, SEP value, or they are more closely spaced, correlation is high. In this case, the SEP will be higher. So lambda by 4 SEP is higher compared to lambda by 2 SEP. Okay. We cannot allow the continuous way of changing the phase. So in practice, only possible case maybe 1 bit, 2 bit, 3 bit, this kind of bits we are talking about. So what will the comparison plot? So let's say you talk about 10 IRS element, but you have only 1 bit control. So 2 option, 0 or pi maybe. In this case, you are here. And when you 3 bits, so you have 8 options, you are here, and you can see the blue curve with this one infinity. So basically it is telling that 3 bits is more than enough. Okay, but when you have increasing your IRS element, typically your 3 bits is more than, it is almost close, but here you maybe you need some 4 or 5 bits to reach into the continuous way of controlling, which is infinite bit, which is not really possible. So so that's another message. Now, in summary, we know this research which started almost 2021 with the SCRB project, and Sumukha and Agrim, 2 research students we were working on. Sumukha was working on this optimization problem, and Agrim with Professor Amrita was focusing on the channel estimation part of it, because that without a channel estimation, really we cannot exploit the advantage of the IRS. And this is how we go, and maybe the next kind of future work can be including the continuous power control, because we hope that continuous power control relieve the shortcoming of the discrete phase shift. So that's any question.
Okay, so in that case, let us thank Professor Priyanka for the talk.
Thank you.
And this also happens to be our last Samvaad of this semester. So I would like to thank right from my co-coordinator, Professor Sushri, and more importantly, the student volunteers who helped us make all the Samvaad talks. And we had a lot of invited talks also this time. So, and last but not least, thanks to all professors and students for attending the sessions and making this a good success. Thank you all, and hope to see you next semester. Thanks. Yeah.